this?
Nothing. Just calculating the fractal dimension of this Lichtenberg figure.
What is a Lichtenberg figure?
A Lichtenberg figure is a fractal pattern formed by running high voltages through dielectric materials.
What is a fractal?
A fractal is a pattern that exhibits self-similarity on many levels. That means when you zoom in, it looks the same.
Got it. But how can I get one of these?
Allow me to show you.
Okay, so I'm going to take you around our setup. So the first step of our experiment is to make our conductive saltwater solution. So we measure out our salt, and we use a measuring cylinder to measure out some deionized water in specific amounts that we calculated to give us the concentrations we desire, which is from 5% to 30% salt in increments of 5. And then we measured out a fixed volume of this saltwater solution into this dish here. And we soak the wood, which is 10 by 10 centimeters, for exactly 5 minutes to control the saturation. And now we're almost ready for our experiment to begin. So we hammer in our nails, fixed separation of 6 centimeters. We connect our electrodes, and then we cover it with this protective box here that makes sure that no one touches the experiment and no fumes escape. And we turn on our fume extractor to remove any dangerous fumes. And then we turn it on, turn it up to 6 kilovolts, and the experiment begins.
When we apply high voltage to the wood, the electric field is strong enough to initiate dielectric breakdown around the electrodes. This means the organic molecules that form the wood, as well as the air and saltwater molecules saturating the wood, are ionized, creating plasma streamers. The plasma streamers propagate through the material, taking the local path of least resistance. As the streamers propagate, they alter the electric field distribution and cause heating and evaporation of the salt water. This increases the resistance, therefore the path of least resistance is constantly changing, creating the characteristic branching pattern. The fractal patterns produced at each electrode differ. This is due to the nature of the streamers. The tips of the streamers produced at the positive electrode mainly consist of slow-moving positive ions and tend to produce thinner, more branching patterns, whereas the tips of the streamers produced at the negative electrode mainly consist of faster-moving electrons and tend to produce thicker and less branching patterns. During the experiment, we noticed that the voltage of the power supply increased throughout the process. This is because the supply provides a constant current, and as the process progresses, the salt water evaporates due to heating, increasing the resistance of the wood. In response, the voltage must increase to maintain the constant current. When the supply reaches its maximum voltage output of 6 kilovolts, the process ends, as the field is no longer strong enough to facilitate the stream propagation and ionization process, given the resistance of the material. At our electrode separation and maximum voltage, the process did not run to completion, which is why the fractals formed at the positive and negative electrodes do not connect.
The reason behind MDF being more successful than the other types of wood that we tried was that MDF is very porous, so it was able to absorb the sodium chloride solution that we'd mixed, which was paramount for this experiment to work, as we needed our sodium chloride solution to form plasma, and this wood simply wouldn't absorb it effectively.
Speaking of soaking the wood, we tried 3 different methods for both types of wood. The first method was to add water on the surface of the wood between 2 electrodes. The second method was to mist the wood lightly with a spray containing the salt solution. The third method, which proved to be most effective and most consistent, was to submerge the wood in 50 mL of water for 5 minutes, and this gave us consistently good and complex fractals.
Let's change the way we think about dimension. Consider this cube. If I now split this cube into 8 identical cubes, the length is now halved, while the mass is 1/8 of the original cube. A half to the power of 3 is 1/8. This is not a coincidence. The index 3 here is the dimension of the cube. We can now generalize this to say that the length scaling factor to the power of the dimension is the mass scaling factor. So the dimension is now log base L of m, and we can use this to find the dimension of any shape.
The first step of our analysis was to capture high-quality pictures of our fractals. We had the president of the photography club do this. We then processed the images using a diffusion-limited aggregation, aka DLA, algorithm. This creates a model of the fractal by converting the image to grayscale, then binary black and white based on a critical shade threshold, defining pixels as occupied by the fractal or unoccupied by the fractal, and releasing particles into the fractal from an initial seed point. They will diffuse by performing a random walk and will adhere if they are in proximity of the particle cluster formed around the seed point. In this way, the model grows from the seed point to form the fractal.
In our project, we employed the box counting method to analyze the fractal dimensions of irregular and imperfectly rough figures. This method is particularly effective for determining the fractal characteristics of such shapes. To implement this technique, we followed a systematic approach. First, we processed the image to extract the fractal patterns in the figure. Next, we placed the processed figure onto a grid. We then counted the number of grid squares required to cover the figure. This counting was repeated as we scaled down the size of the grid squares. For each new grid size, we measured how many boxes were needed to cover the figure. After collecting this data, we plotted a log-log graph of the number of boxes required against the inverse of the box size. It is important to note that we use the length of the boxes rather than their area for this calculation. Finally, we determined the fractal dimension of the figure by calculating the gradient of the resulting plot. Through this methodical approach, we were able to quantify the fractal dimensions effectively and conduct subsequent analysis using the data.
After processing the images, we began data analysis. We applied a box counting algorithm to the DLA modeled images to retrieve the fractal dimension. Then we found the mean fractal dimension at each salt concentration for both electrodes. We then plotted the mean fractal dimension against salt concentration for each electrode and found that there was a negative correlation between these two variables. At a 15% significance level for the positive electrode and a 3% significance level for the negative electrode. This negative correlation matches our hypothesis, as a higher ion concentration decreases the dielectric breakdown threshold of the wood and increases conductivity. This allows the streamers to propagate more quickly, leading to the formation of more linear and less branching pathways. A higher salt concentration also increases the homogeneity of electric field within the wood, further reducing streamer branching. We also calculated the correlation between the fractal dimension at the two different electrodes, obtaining a correlation coefficient of 0.95, representing a positive correlation at 1% significance level. This makes sense, as the electric field between the electrodes is typically symmetric, meaning conditions for streamer formation are similar at both electrodes.
When we used our highest salt concentration of 30%, we observed a very interesting result. A fractal did not form. However, the first thing that happened was that the voltage on the power supply almost instantaneously reached 6 kilovolts. This was way quicker than with any of our other experiments where fractals were successfully formed. And what was remarkable about this experiment was that we observed corona discharge at the positive electrode. We believe that this occurred due to the very, very high conductivity of the 30% salt solution, allowing not only the solution to be further ionized, but the air surrounding the positive electrode, therefore allowing plasma to form. For future experiments, we would aim to take more data relating to our current hypothesis to support this. However, we would also like to investigate the effects of soaking time on the formation of these fractals, and this would allow us, as a result, to obtain fractals in less porous woods. We would also like to investigate the effects of different electrode separations in further detail and its implications for the formation and propagation of our fractals.
It was challenging, but very rewarding to witness our persistence pay off with these beautiful Lichtenberg figures.
We look forward to expanding our research and learning even more about these fascinating patterns.
Thank you for watching and joining us on this journey. We hope you enjoyed this video.